So let's get started with chapter 6. Okay. We are starting with chapter 6. However, the first lesson here, if you notice, is 0.6, meaning this is from chapter 0. Yes, your book has a chapter 0. Oh my gosh, why did we never know this before? Because chapter 0 is just, basic review of things that you already know. It's an introduction to each of the chapters, basically. And until we get to matrices, we really don't need an introduction because you've already been introduced to them your whole life. Except for chapter 6, we do need that initial introduction from the beginning. And cleverly, 0.1 is an introduction to chapter 1, and they're very clever that way. 0.6, haha, is an introduction to chapter 6. So that's the first section we're doing. All right, so we're going to be talking about matrices in this chapter. First of all, let's talk about, just definition, right? A matrix. What the heck is a matrix? It's not the movie. It's a way of organizing information. In fact, it's a rectangular array, and it could include either variables or constants or both, arranged in rows and columns. Every math teacher's dream, right? And it is enclosed in brackets, okay? Each value in a matrix is called an element. Back in the day, or in other books, it may also be called an entry or an element. Those are synonyms, right? So let's first talk about what a matrix looks like. I just mentioned that matrices are enclosed in brackets. Sorry, in some books, they're also in, like large parentheses like that. Okay, let's talk about specifics of a matrix. As I mentioned, each matrix has its rows and its columns. And when we talk about the size of a matrix, we don't use the word size, we say dimensions of a matrix. The dimensions of a matrix are basically just how many rows and columns a matrix has. And the order is always kept so that it's rows first, columns later, right? And if you see here, we've got 1, 2, 3 rows here, right? So 3 rows and 4 columns. And if you get confused between rows and columns, just remember, like in Greek architecture, those long columns, right? These are like tall standing columns, right? So the columns are these right here. So since this matrix has 3 rows and 4 columns, we say its dimension is a 3 by 4. 3 by 4. That's how we read it, not times by. Okay, and normally the number of rows is the letter M, and the number of columns is the letter N. So in general, we say an M by N matrix. Okay? Okay. Now, each of the elements then also has its special name, right? So if I were to look at this element here, number 3, where is the spot for element 3? Well, element 3 is in the second row, the second column, right? That's in the second row and the second column. So how are we going to label that? Well, here is how we label it. The matrix itself always has a name, usually a capital letter. So this matrix is capital A, matrix A. That entry, right, because it is inside matrix A, it's got a name of little a, and its label is 2, 2, because it's in row 2, column 2. There's no need for commas right? We're not even going to be dealing with double-digit rows or columns, so that's good enough. Okay? Ezra?
Oh, I was going to ask you about double digits, but it's okay.
Yep. Okay, so take a look at example 1 here. We've got this, very large matrix. So first it says to state the dimensions of A. Well, let's see, we've got 1, 2, 3, 4 rows and 3, 4, 5, 6 columns. So this is a 4 by 6 matrix. Right? And so you realize if you had said 6 by 4, it would have had 6 rows, 4 columns, right? And it would have looked very different, right? It's like that matrix lying on its side. So you really can't mix them up. Okay? All right. Find the value of the following elements. So A, 2, 3, row 2, column 3, that's 0. A, 3, 5, third row, fifth column, that's 5. Right? 4, 6, that's that very last one here. A1, 2, first row, second column, -3. Okay? Questions? All right. Let's talk about some special matrices. A row matrix is just that. It's a matrix that just has one row, right? So for example, here, this is a row matrix. The dimensions are 1 by 4, and that's cool. A column matrix is just one column. Like here, this is a 2 by 1, 2 rows, 1 column. A square matrix has the same number of rows and columns. So it could be a 2 by 2, a 3 by 3. Generally, it's an n by n. That's how we say it. A zero matrix is any matrix in which every single element is 0. That's it. It could have any size. It's just everything in there is 0. Why do we need a zero matrix? Well, why do we need a number 0? It's for the same, it serves the same purpose. Okay? Okay. An identity matrix. An identity matrix is, here it's a matrix, but I want to specify that it's a square matrix in which every element in the main diagonal is 1. Okay, so what the heck is the main diagonal? Well, take a look at this matrix here, a 3 by 3, right? Look at this one. This is the entry in position row 1, column 1, right? That's the initial entry. If you follow that diagonal down, that is the main diagonal. An identity matrix is a square matrix like that. Each element, every single element in the main diagonal is 1, and then everything else is 0. These are all or nothing deals, okay? Why do we need an identity matrix? Well, you will soon see. It's actually, kind of a VIP in the matrix world, okay? All right, let's talk about some basic matrix operations. We know how to deal with numbers. You know if you have 2 numbers, how to add them, subtract them, multiply them. With matrices, things get a little bit complicated because they're not numbers. They're different beings, if you like. They're different species. First, we're going to talk about adding and subtracting. And they can only be added or subtracted if they have the same dimensions. That's it. All or nothing. 2 by 3, 2 by 3, period. Okay. How do you add them? Now that they have the same dimensions, right? Here's what you do. You have matrix A and matrix B. You take one entry or element here. You take the corresponding element there. Now, in each case, it's what we're taking is in row 1, column 1, right? You add them up, A plus C, and you put it into the same spot, row 1, column 1. That's it. Okay? Same with subtracting. Let's do one. Look at what you've got here. In example 2, you have 3 matrices, A, B, and C. And the first one says to add A plus C. Is that something we could do? No, because they don't have the same dimensions, right? This is a 2 by 2. This is a 2 by 1. So you can't add them. So you just say not possible. That's it. That's all you need to say. Next, I want to do B minus A. Well, B is also 2 by 2. Yay, right? That's a happy couple. So let's do B minus A. All right. I'm going to write down B minus A. Do take the time to write them down, because sometimes you just kind of get like turned around with them, right? If you're trying to skip a step. Okay, we have 2 by 2s, so my result is also going to be a 2 by 2. Okay, so here's what I do. This one corresponds with this one. Subtract them. 10 minus 2 is 8. Okay, this one corresponds with this one. Negative 2 minus 5, negative 7. And you can be a rebel and go out of order. Like, look, I'm going to do this one next. 16 minus 3. Just make sure to put it in the same spot. Okay, in the correct spot. Last but not least, negative 3 minus negative 1, negative 2. That's it. That's how we add matrices. How fun is that? Okay. Scalar multiplication. All right. So again, the world of matrices is a totally different realm than the world of real numbers. It's literally a different realm. And what we do in like 2 to 3 lessons here, it's actually the concept of matrices is actually a whole field of mathematics on its own. You will take entire courses on this stuff. It's called linear algebra. And so it's got a whole structure of its own. In this realm, the matrices are, the VIPs. These are the people who run the town. The scalars, these are numbers that are just lonely numbers. They do not belong to any matrix. They're just random lonely numbers floating around. They have, like a lower precedence than the matrices do. Okay, so there's like the scalars. There's like the matrices, and then there are the scalars. Okay. So a scalar is a number that is just a constant, basically. And you can multiply a matrix by a scalar. It's very easy. Basically, if you want to multiply this matrix by negative 3, all you do is multiply each term inside by negative 3. That's it. So if I wanted to find the product here, it's negative 3, negative 15, 0, 6, 18, negative 12. Okay. Questions? Okay. Some of our other properties that apply to real numbers also apply to matrices. The commutative property of addition only applies to matrices. The associative property, and then the distributive properties, they all apply. So you can manipulate them in the same way. Okay, what does that mean? Take a look at what we have here, A and B, right? We want to find 3 times A and B. Well, the idea is you can do that operation just like you would have done with numbers. If these were all numbers, what would you have done? You would have done the parentheses first and then multiplied by 3. We can do the same thing here. So here's what we're going to do here. This is 3 times A, 5, -2, -1, 0, 3, 2, minus B. Do you see like how the grouping symbols work, right? In math in general, we always alternate parenthesis, bracket, parenthesis, bracket, parenthesis, bracket as you go, in to out or out to in. Okay, this is 3 times. Let's subtract the inside matrices. I'm going to get 5 minus 1, 4, -2 minus 0, -2, -1 plus 2, 1, 0 minus 3, 3 plus 1 is 4, 2 minus 6 is -4. You guys okay so far? And then I can multiply the 3 inside, so I get 12, -4, 3, -9, +12, and -12.
Isn't the -4 -6?
It is. I knew I got in my mind, subconsciously, I knew there was something, so I paused for a minute, and then I was like, no, I'm good. How many of you guys are taking chemistry now or have taken chemistry before? Have you done, when you do the orbitals, those numbers like L, N, M, right? Guess what those are? Those are solutions to a matrix. That's what those are. That's where they come from. There is a math, there's a whole math that goes with it. There's a whole matrix that goes with it. And then that's where it comes from. Spin plus a half minus a half. It's the solution to a 2x1 matrix, guys. These are fabulous stuff. I love this whole matrix stuff. Linear algebra has got to be one of my ultimate favorite fields in mathematics. Seriously.
This stuff is all over computer science.
Yes, it's all over. I mean, the possibilities for a matrix are endless, I tell you. Yes. Okay, moving on. With matrices, we can also solve equations. Okay, so you remember how back in the day, when things were simple, we had equations that looked like this. And then what would we do? Add the 6 to the other side. And get 16, sorry. I'm just so excited about this matrix stuff. And then, x is 16 over 3. But what was the point? When you solved this, everything inside the 3, the x, all of them are numbers. And when you solved for x here, you got x equal to another number because this whole thing existed over the domain of real numbers. But you can do the same thing for matrices, except in matrix equations, when you have x equal to something, it won't be a number, it will be, okay? So, how do you solve a matrix equation? We algebraically solve the equation for x, and then we substitute any matrices. Okay, is my voice cutting out at all? Am I frozen at all? A little. I don't know what's going on. Okay. So look at what we have here. I have matrix A, matrix B, and I need to solve this. Okay. So look at this. This is not a typo. That X is a capital X, and it stands for a matrix. So all I do is I write down my equation, solve for x, so I add a, 2x is a plus b, and then I divide by 2, that's like multiplying by a half. So capital X is 1/2 a plus b, right? Again, that's a capital X, and it stands for a matrix. So now I say capital X is half times A, -1, 2, -1, 4, 2, 3, plus B, okay? And then you do your math. So X is half of, what is it? 4, 2, -2, 8, -4, 10, multiplied by a half, 2, 1, -1, 4 minus 2, 5, and that's your X. Okay? So in the world of real numbers, when we solve, we get real numbers as solutions. In the world of matrices, our solutions are matrices themselves, or can be matrices themselves, okay? Now, that's all I'm going to teach today. And the homework here, because this is from section, because this is from chapter 0, this is what we were talking about before. The homework, right? Look, it's from page P27. Oh my gosh, where the heck is that? That's not a typo. In your book, you may or may not know this, before page number 1, there is a whole other section in the P's. And so this P is before page 0, if that makes sense, right? So it's in the very beginning of the book. It's in chapter 0. So that's not a typo. It's not in page 27. Make sure when you're doing the homework tonight, you're actually working on matrices and not some random equations. Okay? All right. Before I let you go, I do have something else to mention.